right. So today we're going to start. Uh, I would say it's a different topics. Okay, it's we move on from thermodynamics. Right. So now we pretty much travel back a little bit to mechanics, which we will start with something about oscillations. All right. I think I forgot to put the subtopic here, but we're going to do oscillation as well. Okay, so there will be oscillation, and of course, we're going to have a simple harmonic motion. So I'll explain that abbreviation a little bit more. So we'll do a little bit of movement, which is this time is going to be a periodic movement. So I think you haven't done that in the physics one before. So we're going to do it today. All right. However, to make this topic a little bit, well, I wouldn't say compact, but because it's actually is a well, it's a long story pretty much. But the reason that we put these oscillations before the another main topics, which is waves, because they are closely related. All right. And we're trying to make some connections between something that move back and forth, then eventually that movement can generate something that we're going to call it the waves. All right. And that we will do that afterward today. Okay. So we're going to see how the oscillations and waves are related, and how we're going to use mathematics to describe these two phenomena here. Okay, so that will be it's kind of fun. I kind of like it. All right. However, the today's topic will be, well, another kind of mathematics that we're going to use, and it's kind of good that this kind of math will eventually sort of, well, you'll see this kind of math so many times in your life, I think, because in our lives we deal with something that movement or whatever the behavior is periodic very often, like electromagnetic waves. Maybe those computer engineering and computer science people have to deal with, because the it's the electromagnetic waves, it's waves anyway, so we have to still be dealing with that kind of movement anyway. All right, and the mathematics will be pretty much related, so it's kind of good things that if we understand things that we're going to do today, I think it's worth it for your future, I guess. All right, we'll see. I'm not sure that I will be able to complete them all in terms of the amount of material today, because I think I'm going to explain a lot of mathematics in terms of the usage of the function that I'm going to start talking right now. So we'll see. All right. So I'll go as far as we want. Well, to at least you should be able to do the homework. All right. But maybe the last topic, which is about the linear wave equation, I'm not sure if I haven't tried this before. So we'll see. Okay, let's get started. So what we're going to do today, let's start from Newton's law. Okay, you guys have done that, a lot of it from previous course, I guess. So you should be able to do this very easily. However, the system that we're going to look at today is the mass on spring. Okay, so if I have a mass M attached onto a spring, and if it sort of like pull it down a little bit, eventually it's going to move back and forth. Okay, so what I'm trying to sort of give you an idea of how things goes is I can actually, okay, let me sort of, all right, if you want, you can try going to online simulation. So I'm going to try something because I did try this before. However, it turns out the the refresh rate of this whole sort of Zoom thing might not be as good. So I'll show you what it means. So you guys can try. You can just search like SHM, all right, and then you can do like simulation. Okay, all right. So SHM eventually will come down to the simple harmonic. All right, so we'll see that soon. So that is simple harmonic mass on spring. You can try a couple of simulations there. However, the one that I like is, okay, let me do spring. And I can do PHET, that is the Physics Education Simulation Lab from Colorado University. And that was, I think that's the first one. All right, so I can try that. Okay, all right. So let me know if you guys can see this simulation sort of like in real time. I tried it in Google Meet. It didn't go as well. It's sort of like, because it doesn't really give good refresh rate, so you don't see the simulation continuously. You see only like a, you know, just a flash of picture. So that wasn't so good. All right, but anyway, so it seemed like Zoom might be a little bit better. We'll see. All right, so I'll go full screen. So the key is I have a spring, okay? What I can do is I can pull a mass in there and let it go. Okay, so it's going to bounce back and forth. Okay, I can change to a larger mass. Okay, here we go. Oops, sorry, I have to take it out. Okay, let's stop it. Okay, okay, I pulled it down. Let me put the larger one there. Okay, and then I let it go. And I'm going to do it in slow motion. So here we go. So this is what's happening. All right. So of course, I mean, this simulation is in a vertical direction, but it doesn't really matter. All right. We can do it in a horizontal direction or vertical direction. But the key is you will have a point of equilibrium. All right. That is the point that actually the weight of the mass for the vertical case is balanced out with the force from the spring. So the good thing about this simulation is I can actually show you the force right there. So there is a gravity, of course, that's the weight. You guys can see this sort of okay. Just let me know if the sort of animation doesn't look so nice. But if it's good, then I'm just keep going. All right. So at least that red arrow right there, that was the mass. That's of course that's the mass with the gravitational pull. So you get a weight of it. And of course, you get a spring that's try to sort of like balance out this mass. However, if you look at the blue arrow, all right, so that will be the point where, of course, it's not a constant for the blue arrow. So the blue arrow is representing the mass on a spring, okay? Mass, not mass, force, sorry, force of the string that's trying to pull the mass back to its equilibrium point. Okay, so that's what it is. If I try to net these two forces out, so that will be the black arrow. So I do the cancellations between the spring force and the weight. You get this black arrow. Okay, so just take a look at this one for a little bit. Just sort of like staring at it. All right. All right, it's down. The arrow is extended. Now back to the equilibrium point. The arrow is extended up. I mean, on the way up, it's extended, come down to zero, extend it again. As you can see, this net force right here, trying to pull the mass toward the equilibrium line. Okay, so this is what we're trying to say. This is, we call it the restoring force. The reason it's restoring is because it's trying to pull the mass back to the equilibrium point. See, the direction of the force always point towards the center of it. All right, so this is the kind of the nice thing. And this is the main behavior of something to be a periodic motion. Everything that has a periodic motion, it must have a restoring force, because it must be a force that's trying to pull things back to the center of the movement. So you cannot escape from it. You have to come back. And if you want to go the other way around, I mean, you're going to get pulled back to the center, right? So that's why it's going to be oscillation or periodic movement, because you cannot get away from this restoring force. That is the key of the periodic motion. Okay, sounds good? All right. And of course, among this thing, right, you can draw anything you like. For example, I can show you the velocity. That's a green one. So of course, you can see that now the velocity is getting maximum at the equilibrium point. All right. So once again, just staring at it, sort of like get it, sort of, sink into this whole animation right here. So of course, at the lowest point, okay, the arrow go to zero because of course that is a point of return. So at the highest point, the arrow go to zero because that's another point of return on top. So at the lowest point and the highest point, that is a point where the mass decided to sort of change the direction of motion. And that's why at that point, the velocity has to disappear because it's changing the direction. So the magnitude of the velocity has to hit zero. Okay, make sense? So this one is just like when you throw something up into the sky, at the highest point, the velocity has to have the magnitude of zero. Okay, because it has to turn around, something like this. Okay, another thing that you can add on top, of course, okay, let me erase this velocity. I can go acceleration if you like. So right here, once again, the orange arrow represents the acceleration. But this one is sort of like intuitive because we have the Newton's second law. Yeah. So that means sigma F equal to ma. Because we already said the black arrow was the net force acting on this mass. So whatever the force is, there must be the acceleration pointing in the same direction. So there's no doubt. The acceleration that the mass is having must be the same direction as the net force acting on it, which is right now is only the net force uh, from the spring and the weight. Okay, sounds good. All right, and then I can combine this whole thing. Then this is sort of like a things that supposed to sort of running in your head every time you're thinking about the periodic motion. But we're gonna go with the simplest case. We're gonna go with the mass with spring attached on it. That's the first case that we're gonna sort of do the mathematical analysis in detail. All right, but this is the main sort of like scenario that you're supposed to have this in mind at all time. All right, otherwise then, well, it's gonna get sort of like confusing if you try to just looking at the mathematics on paper. All right. So I'm just sort of having fun doing this. I mean, for you guys, sort of like if you kind of think of this movement in your head all the time, all the time. All right. And just to complete this whole thing, I can put a displacement on it. Here we go. Okay. But this one is things a little bit complicated because we're doing things in a vertical direction. So every time that you do everything in vertical direction, you always have the gravitational pull. All right. So that's why the displacement that they are doing right here is kind of like it's a displacement with respect to the unattached string or spring. So it means it's like a natural length of the spring that has no mass attached to it. So that's kind of like, well, this one is not what we are going to try to do. Unfortunately, I don't see that people love to do it on the horizontal direction, but we can do, I mean, for this simulation website here, they don't do it on the horizontal surface. All right. But I hope this one showcase a good stuff right here. Okay. Sounds good. All right. If it is nice, then I will do it one more time. Okay. So let's do Shm simulation again. I have a couple of simulations to show you today. All right. So I'll try to go as slow as as I prefer to go slowly here because it's very important for you to have sort of intuitive understanding of the situation first. All right. And once I overlay on top of this with the mathematics, everything will be clear. I hope. Well, try me. Okay. I hope it works. Okay. Another one that is very nice. This is another nice website for you to do some simulation or there is some animation that's representing something is the oralphysics.com. All right. And once again, I hit on that. All right. And this one lead you to the simple harmonic motion with mass on a spring. Okay. And it has the mechanics of the algebra from Google. I think they have that kind of thing here. So the nice thing about this one is, okay, let me do full screen here. All right. Where. Full screen. Oh, I don't know how to do full screen here. Oh, Oh, I cannot do it on the, okay. Well, I might not have that option on the tablet here. Weird. Okay, I don't have keyboard. Okay, all right. So what you have over here is, right. Okay, let me get rid of this curve for now. All right. So we'll come back to that, right? This graphing thing will be very useful later. Okay. So what I can do is I can have the initial stretching. Okay. So as you can see, and because this mass block is so big, so let me reduce it down a little bit. All right, here we go. All right. All right. And then I can run this simulation. So what you can see is the parameter that I need. There are three things. If you look on the left side of this animation, there is an initial stretch. So I can adjust that. Okay. What is a stretch? All right. And the arrow in the middle that represent the equilibrium points. So when everything is on ground, thing is a little bit easier because you don't have to worry about the gravitational pull anymore. So it's purely from the spring. This is the only force that acting on this mass. Everything else is on a vertical direction. So there is a normal force pointing up. There's an mg pointing down. We don't care because everything is on the horizontal direction. Now that's good. So once you stretch the string, you're gonna get the vector, right, of the force on top of this one. So let me annotate this. So we're gonna have some force pulling it backward right here. Nice. Okay. So that's what you get. And I run this simulation, of course, it's gonna bounce back and forth. All right. It look a little bit jerky, but it's on mine too. That's not because of the zoom, because when I look at the tablet, it doesn't have a smooth movement just like the previous simulation. But anyway, you see the whole point, right? So if we're gonna go this one slower animation, might see a little bit better. So this is what's happening. All right. So you have x equal to 0 that is at the center. Okay. You have the maximum on one side and another maximum on the other side because that will be the biggest displacement that this block can move. Right. But it's going to bounce back and forth because the spring try to pull things backward to the center all the time. Make sense? Yeah. All right. Very nice. All right. So we're going to stick on this and now turn to our slide. And I'm going to put mathematics on top of this and we'll see how it goes. I don't know if this helps or not, but I hope simulation works quite well. Okay, here we go. Now it's crunch time. So what actually happening is just Newton's law, nothing more. All right, and we're gonna do a simple case. We're gonna do mass on a spring on the floor. So we're gonna do a horizontal movement over here. So as you can see, the only force acting on this mass is just the spring force right there. Okay. However, if we're going to follow Hooke's law, right? You guys sort of very remember the Hooke's law. I just write it down here. So that's a Hooke's law. Hooke's law. So force depends on the stretching or the compression. So it depends on the distance away from the equilibrium point, the x. Okay, the further away, the force from the spring will be larger. That makes sense. Okay, the negative side is just to represent that, hey, everything has to point towards the center, point towards the equilibrium point. All right. And the K right here, we called it the spring constant. Spring constant. And this constant representing how stiff the spring is. Or, I mean, if the spring is so stiff, it means it can sort of give you a very strong push and pull. So we call it a stiff spring. So the K is big. But if you have like a super loose spring, it's very like, soft and everything. So that means the K is small. So you're not going to get a lot of push or pull from the spring. Okay, sounds good. All right, so the spring constant tells you the stiffness of that spring. So you can think of it like if you do like a car, like automobile shock up, like the super like tight spring, that is going to be a very high K, high spring constant spring. But if you do like a spring, like I don't know, well, I don't have the spring around here. All right, but anyway, so you have some very soft one, the K is small. So that's it. That is the only force acting on the mass. So if I draw a free diagram, free body diagram, that will be the only force acting on this mass. So that's it. I put it there, minus kx. Okay, so the x is just the displacement right here. That's just the displacement from the equilibrium point. So minus kx equal to ma. I'm done. That's it. That is the Newton's second law. Okay. Now I can move things around if you want. I can sort of say, okay, what is the acceleration at point x? So I say I just move m to the other side, negative k over m over x. However, here's the key stuff of today's lecture in the morning. However, everyone knows that the acceleration is the second derivative of the displacement, right, of the position. So that means if you do second derivative of x with respect to time, that is your acceleration. Okay, so I'm going to express that here. Now here comes the question. What is the x from this equation? What you are facing right here, we call it the equation of motion already, because you get this equation directly from the Newton's law. Done. However, we have a duty to solve this equation. And now this equation is the second order differential equation. Here we go. All right. Now to make things a little bit cleaner, because I don't want to keep writing k over m, k over m. So let me just call k over m omega squared for now. All right. I'll come back to this later. This is a very important sort of naming. However, for now, let me just call the factor in front of x to be omega squared. Okay. All right. So my attention goes to this. How can you solve this equation? The green box right here. Okay, let me try something here. Before we move on, you have to solve differential equation, all right? Because we don't want to go back to technique of solving second order differential equation. I think you saw this from maybe calculus 2 or maybe calculus 3. But I'm going to say it simply. What kind of x that you're going to get? When you differentiate twice, you get itself back. You get back the original with the extra negative sign. That's it. Makes sense to me, right? What kind of x? What kind of function? What kind of function of x? That once you differentiate twice, you get the original back, but with a negative sign. Now you go back in your life. If you notice, the function that you have studied since maybe whatever middle school, you only have polynomial. Okay, you have logarithm, you have exponential, and you have trigonometry function. Your life pretty much like sort of like, you know, dealing with this kind of thing. Mainly, there will be some weird functions, you know, complicated one, absolute. I'm sorry, okay, just park it there. But in terms of the family of function, you probably dealing with polynomial. That will be the easiest one. The x squared, the x cubed, on and on. The logarithm, okay, you learn that, log of x, on and on. The exponential, you can do like a to the x, e to the x, whatever things, and trigonometric function, sine, cosine, tangents, you know, everything. What class, what family of those functions give you this property? You said there's only one thing. It must be either sine or cosine. Nothing else. Polynomial fails. Every time you differentiate polynomial, the degrees drops down all the time, right? Logarithm is gonna get as bad. Okay. Oh, instead of talking just like that. So if you differentiate x squared, okay, by the x, you get 2x. So the powers just sort of keep disappearing on you. Differentiate log of x, you get 1 over x. So eventually you get to the power function of x anyway. So fail. Now you probably think of what about exponential then? It's nice. the derivative of exponential give you back the original, but you are missing the negative sign. You don't get the negative sign from the exponential. So you only have one class or one family of function left, and that is trigonometric function, sine or cosine. All right, so I will show you right now. So if I do dx, okay, this is a function of time now. All right, so even though on the left, I just represent it as a function of x when you do calculus. But for now, this x is a function of time, t. So when I do first derivative, you got cosine omega t. Make sense? Don't forget, chain rule. You have to differentiate whatever left in there. So you have to do d omega t by dt one more time, right? You guys remember this. So that means you're going to get extra factor of omega out to the front. Okay, and I will do it one more time. I differentiate that one more time. There you go. Here. So what you're going to get is I'm going to differentiate the omega cosine omega t one more time. Omega is there. Derivative of cosine, you get negative sine. And don't forget to derivative of whatever the argument inside one more time, the chain rule. You get extra omega out. Everyone with me so far? Okay. And that's it. This is what you get, negative omega squared sine omega t. But when you look at this one, Mokhetan, that is right there. Sine omega t, that is your original starting point. Perfect. You now know in your head, this kind of thing will work for solving this second order differential equation of this kind. Okay, you can do it with the cosine as well. I don't care, because when you differentiate cosine, you get negative sine. Derivative of sine, you get cosine. So you can start from either sine or cosine. It's pretty much the same thing. So pick one. You can use any sine or cosine. It works. Okay, so I spent like half an hour trying to explain the setup of the simple harmonic, or I mean the oscillation from mass on a string, along with the mathematics behind it. But as you can see, these whole things sort of like spring out in your face directly just from the Newton's second law, sigma F equal to ma. That's it. So that is a powerful stuff from the Newton's law. That only thing that you need is the equation of motion. But because of this equation of motion is a differential equation, so you have to pretty much, solve that differential equation. However, by the form of this differential equation, the answer must be in the family of sine, cosine. It's a trigonometric function. And now you start to see why it's a periodic automatically, because it's a sinusoidal function. It sounds good? I don't know, is that too long? But I hope I try to sort of go slowly at first. However, that's not done. If this is good, then, well, at least you get a glimpse of what is going to happen. But everyone try this. If I put a constant in the front, is it going to be the solution of that original equation of motion? The answer, of course, must be yes, because I sort of put it there. So let's do it here. I'm just going to write it just prime for the derivative. Just make it a little bit shorter. So later on, we might just use x prime and x double prime to represent the first and the second derivative. Okay, so if I do this, the dx by dt, the a is just a constant. And if I start from the cosine, the first derivative will give me the negative, okay, sine omega t. However, don't forget the chain rule. I get extra omega right here. Okay. And if I do it one more time, so I do the second derivative of that. So that will be my x double prime. The a is still there. I haven't done anything. Okay. And the derivative of the sine is the cosine omega t. And I get extra omega out from the derivative. So I get 2 of the omega right there. And of course, if I rearrange this a little bit, negative omega a cosine omega t. Now I'm getting the original back. You see? Along with the omega square, just like what we like right here, omega square. Perfect. Okay, still so far so good. So that means actually a cosine omega t is a good solution. It's a good one. But that's not done yet. Let's do one more time. What about if I have a cosine omega t plus some constant phi? All right. Some of you start to see that, oh, it's not going to change a thing because when you add some constant inside the argument of sine and cosine, the chain rule has no effect on this. You're not going to get any extra stuff from it. So let's do this one together. So I'll do x prime, derivative of this. A is constant. Derivative of cosine is sine, negative sine, of course, omega t plus phi. But when you do the chain rule inside, that's mean when you want to have to take the derivative of omega t plus phi, you only get omega out anyway. The phi is just a constant, so it disappears. Okay, so that's nice. I haven't done anything much. I can do it one more time. X double prime. Okay, A is constant. I haven't touched it. I keep negative omega there. Derivative of course of sine is cosine. And when I do the chain rule, I get extra omega out. So it's omega square in the front. Very good. And then I can rearrange this negative omega square a cosine omega t plus phi. And once again, you go back to the original scenario. Your original function is back with the omega square in the front, negative signs there. Perfect. So actually, this is good too. Okay. All right. So my point is the way that you're supposed to do this, you have to pretty much try to write the final solution to be as general as possible because you want to be able to have a solution that can describe any scenario that you want. What kind of scenario that I'm talking about right here? In some textbook, or well, I would say I have seen before in maybe like high school textbook, they might just already content with this solution right here on top. A cosine omega t is kind of nice. However, if you plot this curve, it will be the curve on the right. Everyone know the cosine function is the function that starts from the top, right? Cosine, you start from the maximum. So it's mean when you substitute t equal to 0, cosine 0 is 1. So right here, cosine 0 is equal to 1. So that means x at 0 is a. So if you pick the cosine to be your solution, that means you are representing the scenario that you're starting from the top. However, in real life, well, I don't want to start from the top. Maybe I want to start from the 0. I want to start from the bottom. I want to start from somewhere that I like the second curve right here. Like, well, I want to start somewhere in between, something like that. And that gives you the flexibility of your starting position. That's why I'm going to represent sort of like I have to add on top of this that, hey, you might want to start from some angle phi. So that's why you can call this like initial phase. Okay, or in some case you can call like a phase constant or something like that. So it depends on the context. But the point is the phi representing what is going on when t is 0. See, when t is gone, that phi is still there. So it's just telling you what is going on with the initial position. Okay, initial position. You don't have to start from 0 all the time. You can start from maybe 45 degree, pi over 4, 90 degree, pi over 2. You can start from any angle that you want. But in physics, we don't want to call it the angle because that was the main stuff that you use in geometry. But for us, the angle represents the position on the movement. So we try to use the word phase instead. All right. But in your head, the phase or the angle, they are pretty much the same thing. Does that make sense? Sort of like get some relation here, you guys. Okay, no, I cannot see your face. I hope This sort of give you some introduction to the sine cosine function. All right. So if you understand this sort of infrastructure that we're going to use, then once again, come back to our curve right here. Don't forget the horizontal curve right here is time. Okay. The vertical one, we represent the displacement. We use x. So if you look at the horizontal or the x-axis right now, the time scale, it means if you're starting from some point, eventually it will come back to the original point because it's a periodic motion, right? It's periodic. It will come back. It will come back. It will come back. So if you measure the time it takes to complete one round of a motion, we call this period. That's why we call it a periodic, because there is a period of motion. There is the constant amount of time, the fixed amount of time for you to complete one cycle. We call it a period. Okay. However, because this is the time, okay, let me put it on here. This is a time per cycle. You can do the flip over to get to this. This is a cycle over time. With me? Right? The period is time per cycle. So if you flip over, it's going to be cycle over time, just a unit sort of flipping. The cycle over time, that's just the frequency. How many cycles you're going to get per second, okay? So that's why you have a first simple relationship between the period and the frequency is the inverse of each other. F equal to 1 over t. You probably have seen this from circular motion, yeah, back in physics 1. So that is the, when you do circular motion, you complete one round, you call it the period. And you flip it over, you know how many rounds you're going to get per second. That's frequency. And once you have that, then you probably sort of recognize this right away. If you have the frequency, I can turn that frequency into angular frequency. You guys with me? So let me put that sort of formula on the side. The frequency is the number of rounds per second, but everyone knows when you complete one cycle, and if you think in terms of the angular position, one round or one cycle, that's 2 pi. So all you need to do is just multiply by 2 pi. You turn from the number of round, okay, which is a number, into radian, into the angle, unit of angle, radian. So all you need to do is just multiply the frequency by 2 pi. You turn just the simple frequency into angular frequency, the omega. So that's why I have another expression right here for you guys. Omega is 2 pi over period. Done. Okay. So now you know what is going on with the frequency of the oscillation. Okay, how quickly it goes. Or you can talk in terms of how long does it take to complete one cycle. It's your choice. You can talk in terms of the frequency, or you can talk in terms of the period of motion. And the frequency, you have two choices. You can do angular frequency or just a regular frequency, number of cycle per unit time. All right, it looks quite a lot, but I hope it works. All right, just let me know and you can give me feedback if this one is sort of like too fast or too slow. All right, next. That's kind of fun, yeah? So what I'm gonna take is this. So this is going to be my general solution to our second order differential equation that we obtained from Newton's law. That's it. This is your general solution. All right. And don't be confused anymore. If you read some textbook, they might write it as a sine omega t plus y. It doesn't matter. Right? You can pick sine or cosine because you have that phase constant adjustment right here. All right. And sine and cosine is exactly same shape, but it's translated by just a little bit. Okay. So no big deal. You can pick sine or cosine. They sort of equal footing now. No difference. All right. But because I want to stick with the reference text, textbook that we use, they use the cosine function. So let's stick with the cosine. And the good thing about in our scenario is we pull our mass all the way out. We pull all the way out. So it seems like we starting everything from the maximum displacement. So cosine is a good one. Okay, come back one more time. We start everything from the maximum point because we stretch the spring all the way out, and we call it that is your starting point and let it go. So at the point of let go, that is your maximum displacement. Okay, sounds good? All right, so that's nice. So this, we're gonna take a cosine omega t plus phi to be our general solution for the simple harmonic equation. Oh, I'm sorry, we haven't talked about simple harmonic yet. I mean the equation of motion. All right. So that means the A itself represents the maximum displacement possible. So we say X max is A. So we call this amplitude. That's your amplitude. The A representing the amplitude. Okay. Now we already showed you this. When I differentiate, once I'm getting negative A omega psi omega t, but no matter what, the psi function will never go beyond negative 1 to plus 1, right? That's the range of the sine function. So that means the velocity will never go beyond positive and negative value of this A omega. So now you know this will be your maximum velocity possible, omega A. Okay with me? So far so good? And now you start to see the trend right here. Whatever comes in front of this sine and cosine, that will be the maximum possible value of that. So if you differentiate the velocity one more time, you get the acceleration. So you're going to get the A omega square A. That would be your maximum acceleration right there. Okay. And I hope that at this point now, you can overlay this on top of the simulation that you saw before. Now, not only you know when and where you're going to get maximum velocity and maximum acceleration, you know the value of it. So it's kind of nice. Okay, so I'm going to show you one more time. Just flash you back to this one. Okay, here we go. See, the simulation is still there. There you go. All right. So the green one gone to zero, the velocity go to zero at both two amplitude. Okay, on the top, we call it the amplitude, right? The displacement. So at the maximum displacement, the velocity is gone. And the green arrow, the velocity is largest at the equilibrium point right there. And now we know it's omega A. And the acceleration, the yellow arrow, give you maximum right there, omega square A. That's just for fun. All right, but that's, now we know what and where and when is supposed to be right there. Okay, very nice. Okay, get going. Okay, everyone sort of follow so far? No, pause that, no, pause that, no. All right. So now here's the nice stuff. Okay, I'm going to put them all together and I'm going to show you that what you just saw right here, every time that you can represent the movement in terms of the sine or cosine function, which is the periodic stuff, we call it the simple harmonic motion. And that's why we sort of shorthand say it's a SHM, simple harmonic motion. So every time that you get something right in solution that can represent the periodic motion by sine or cosine, that motion can be represented as a simple harmonic motion. But now, because we know this solution must come from the second order differential equation of this form right here. Okay, keep this in mind. I am going to show you a little bit more of stuff right here. All right, and I think it's gonna be like wow, wow, wow a little bit. I don't know if it's wow, wow, wow or not, but I think it's kind of nice. Okay, this is the power of mathematics right here. Okay, everyone try this. Okay, I leave you some blank space so you can sort of like, sort of do some writing on your own. So I'm going to do the same thing, but with the different scenario of periodic motion. Another kind of periodic motion was the pendulum, right? The simple pendulum. So if you have a mass attached on a string and you have a fixed point on the ceiling and stuff like that, And then when you slide your mass a little bit on the side, let it go, it's going to swing back and forth. Everyone knows this. But what I'm going to show you, I'm going to show you once again the equation of motion. All right, here we go. Let's get things started here. So at a point, all you need to do is just write out the force acting on this mass. Okay, so you just try to write a free body diagram. You only have two forces acting on this mass right here. Is the mg. So let me highlight it one more time. The rate right here. Okay, and the tension. That's it. So you only have two forces acting on this. Okay. However, because right now your movement is along the curved path, right? Because it's going to be that circle of radius L if the L is the length of the string. So you are actually move in circular path, right? A section of a circle, okay? Back and forth. However, at one particular point, the movement will be in this direction that I sort of put like a sort of directional line over there, and it's a tangential to the circular path. So at one particular moment, the mass is kind of sliding, okay, now, at tangent to the circle. That's what it is. So what I can do right here is, oh, maybe I didn't draw it nicely. Okay, let me draw it over here. There you go. There you go. So what I'm going to do is I'm just going to break the mg into two components, right? So I'm going to decompose the weight, the mg, into two components. One component is downward over here. That's going to be your mg cosine theta. The other component will be the components that point to your left, mg sine theta. And now you start seeing that, of course, the vertical direction will doing nothing because there is no motion along the direction that is a radial direction. There's no motion along the radial direction. So that means the the tension must cancel out the mg cosine theta. Okay, because you don't have any movement, okay, perpendicular to that green line right there. So no, there's nothing moving there. So the force on that axis must go on to zero. So you only have one force left, which is the mg sine theta. And now you see what I'm trying to say before. Can you see this? That you are, okay, let me look at the curve right here. You are right here coming out. Okay, that's your displacement, right? Even though it's curved, I try to put it as a curve, but all right, it's just on there. So there is a displacement along the curve to that point right here. However, the mg sine theta try to pull it back. Okay, and that's perfect. So this is your restoring force, just like we agreed on. Okay, sounds good. All right, so if this is good, Newton's law say mg sine theta negative, right? Because it's pointing backward. It's just ma, sigma f equal to ma. But now your acceleration is just here, the distance along the curve that we call s. So it's going to be the second derivative of s with respect to time. Isn't that nice? Okay, okay. Everyone with me now? So this is the equation of motion of a simple pendulum. Nice. Okay. So what else can we do? Can we solve this? Well, almost there. M cancel. So mass has no relation with this motion whatsoever. It doesn't matter how big of the mass you're hanging. It doesn't come into play. But can you solve this equation though? So let me write it like minus g, minus g sine theta equal to d2s by dt2. Whoa. That's not easy. Okay, because it looks very messy. Well, on the left is a function of theta. On the right is a function of s. Well, John, that doesn't look so neat. However, right here, Here comes the stuff that you have to learn. If you recognize that, I think you probably have learned this back in high school, if you have seen that. Every time you have a simple pendulum and you say, hey, I'm going to treat this as something simple, that is simple harmonic motion. We assume that the angle of movement must be small. Remember, sort of, you have some restriction like this before? Like, hey, the motion must be within small angle. The point of small angle is you can make some approximation when the angle is so small. And the approximation right there, I show you, I already have you this. Everyone look at this table that I prepare for you guys. It's kind of nice. And you're going to use this a lot for computerization, I'm sure. When you do numerical calculations in, do computational stuff, you use this kind of thing many, many times. Okay, so look at this one. We're going to focus on the angle in radian because that's the one that we kind of like. Okay, so when the angle is 0, no doubt everything is gone to 0. There's no big deal. Okay, sine of 0 is 0. That's good. Now let's move on to like 2 degree. Can you see something here? I highlight the blue and I double the second blue here. The angle in radian for 2 degree is 0.0349. And the sine value of that is the same. Isn't that nice? And now you start to see some deviation when you are around like maybe 3 to 4 degree or so. But the discrepancy happens on the 4th digit of the sine of that angle. Can you see that? So the difference is like, well, when you add 5 degrees, 0.1%, which is, well, pretty low. And now you can go up to maybe 10 degree if you like. So if you go up to 10 degree, your error is around 0.5. Okay, maybe this is start to be unacceptable for some. But, well, for us, it's still not bad. Still not bad. If you allow to like maybe 1%, you can even go to like 15%. So that's why in high school textbook, usually they would say to have this sort of the pendulum move in something in simple motion, you will limit your angle of movement to be within 10 degree. That is a reason because you allow the error to creep in to be less than 1%. So that's okay. But one thing that you're supposed to keep in mind, so that's the realistic stuff here. The pendulum that you're seeing over here is not simple. All right. Without this approximation, you're not going to get a simple movement over here. It's not simple harmonic. Right. So if you go crazy about the detail calculation, you have to do computer stuff and you have to do computerization to solve this differential equation. So as you can see, this differential equation that you see over here, you cannot solve by hand. Okay, because it's an angle sine theta and the s on the other side. But if you agree with me that when the angle is small, for small theta, sine theta is approximately equal to theta. That's the approximation that we're going to use. All right, and let's use it right here. Nice. Okay. And now, once you once you approximate the sine theta to theta, now everyone remember the relationship between the theta and the arc length subtaining that angle. With me, guys? Yeah, the angle is just the arc length divided by the radius. So that means I can once again rewrite that equation as minus g s over L equal to, very nice. That's it, guys. That's the point I want to make here. Do you should notice something right now? I can actually wrap this G over L over here. S is there on both sides. And that gives you this equation right here. Okay. All right. So the shape of the function that you have is is a the d2 by dt2 equal to some constant, which is constant in the front right now is G over L. And then I can turn things around whatever I like. All right. Well, Ajahn, you just write it as S over here, but down here is theta. It's up to you because I can parallel with this. I can approximate this as a theta L if you like. Doesn't matter. All right. So that means I can do equally well by keeping the theta and let go of the S. Up to you. But the L is still on the right and I can move to the left. Isn't that nice? So the key point that I'm trying to point out right now is the form of the equation. The form of the equation. D something twice get itself back with some constant in the front along with the negative sign. That is always simple harmonic. That is sort of like the stuff of the morning. Every time you see this equation, you differentiate something. Where does the S over L come from? Okay. One of your friends asked, where does the S over L come from? That is from the definition of the angle. Okay, let me show you here. So if you have a full circle, okay, so let me sort of write this. Everyone knows the circumference of a circle of radius r is 2 pi r. Yes. Okay. And everyone knows every time you go full one round, the angle that you sweep through one circle, everyone knows is 2 pi. That 2 pi come from the angle in the middle, right there, is theta equal to the arc length over the radius. Okay, you guys with me? And if you go one full circle, your arc length is 2 pi r divided by r. That's why every time you go one full cycle, the angle that you sweep along with it is 2 pi. But now you don't want to go that far. You might want to go just some S. You don't want to go full circle. You just only go for S distance. So the angle that you can get, okay, right there, the angle in here, you're going to get by take the S divided by the radius R. So let me do this. Theta equal to S over R. There you go. Okay, sounds good. All right, so that is definition of the angle actually in radian. Okay, in radian. So you take the arc length divided by the radius of that curvature, you get the subtending angle of that arc right there. Okay, now got that? Okay, all right, very good. So come back to our point right here. So my point I'm trying to say over here is, from now on, whenever you see stuff like this, derivative of something, something, okay, twice, get the original back with the negative sign. See, I try to highlight, like, look crazy over here. When you take derivative of something twice, you get the original back with the negative sign. You start seeing things now. Yeah. I don't care. When I say I don't care is it has the common shape of the equation that look like this. Second derivative equal to some number and original with the negative sign. The factor that comes in between, we named it before omega square. So for this case, our omega would be square root G over L. But now you see why I'm trying to relate this whole stuff together. We just named the omega the angular frequency. And we saw this substitution before back in the spring that we named omega root K over M back in the spring. Over here, we have omega equal to root G over L. So that means actually this substitution over here will give you the frequency of motion automatically. Okay, one more time. So the reason we name this one omega is not just for naming, it actually has the physical meaning attached to it. So the omega that we are talking about is actually the angular frequency of these movements, because the omega shows up in your solution right here. So it tells you how quickly the stuff is actually oscillating. Omega that give you the frequency of that periodic motion. So come back to the mass on spring. We say omega is root K over M. See? So nice. So how fast things will oscillate depends on how stiff the spring is, the K. The stiffer the spring, the higher the omega, which makes sense. When you have a stiff spring, you're gonna bounce, 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 bounce so fast. But if the K is small, you got a very soft spring, the omega will be small because everything will go very sort of slowly. Okay. Next, the mass. Okay. When you have a big mass, of course, when things travel, it's going to be tough to move, right? Because the mass is sort of heavy. The omega will be small. But if you have like a very light mass, the spring will sort of go back and forth a little bit more easily. So you get higher omega, which makes sense. Okay, the square root is too bad. It's there because that comes from solving the differential equation. But that's what the omega is for the mass on spring. Now, when you come back here, Ajahn, I can see now, omega is root G over L. So that means the only way that you can change the frequency of your oscillation is you have to change the G. You have to go somewhere else. Go to the moon, go to the Mars, go to Jupiter, whatever, to change the omega. All right. So given that we are on the surface of the Earth, the G is pretty much fixed. So the only way that you can change the oscillation frequency is by changing the length. That makes sense. Okay, because when you try, I should have that here. But anyway, so when you have the length is so tiny, right, things will go quickly. But if you extend that length out, you will see that the oscillation is kind of like a little bit slower. Okay. But as long as you keep the length fixed, you cannot change the omega. Okay. All right. That's kind of neat. Maiwa. I hope. I don't know. I tried. I talk about this like an hour now, but I hope you see the connections between there is Newton's law, of course, and the mathematics. Yeah. And the general form of the differential equation that eventually lead you to simple harmonic motion. And now you attach the simple harmonic motion with the sine and cosine function right away. So from now on, every time when you heard of simple harmonic motion, in your head, you think of sinusoidal function right away, because that is the solution of simple harmonic equation. It's sort of like the words sort of like interchangeably used. You can use it interchangeably. Simple harmonic, sine, cosine. There is the omega, fixed angular frequency, on and on. They're pretty much, within the same context of simple harmonic motion right here. All right, but yeah. Okay, all right. But that's not done yet. No. Okay. But it's still the same stuff. Look at this. All right. I will treat with one more system and I will show you what does it mean by only things that you care about is the form of the differential equation that looks simple harmonic, and your life will be very good. Okay, try this. Okay, so this one, you can write the equation of motion, but this one, you have the system of the mass that has the size. So you don't have just like a pendulum anymore. I think you call this one physical pendulum. So the way that you can do this is you can use the Newton's law, but in the case of rotation. So you use the second law of motion in the how do you call? I think you call it like extended mass. Okay, you have a mass with a shape now, not just a point mass. So what you can do is you can calculate it through the sigma torque, okay, equal to I alpha. Yeah, sort of like ring any bells here. Okay, because now you have the um the torque acting on this physical mass right here. Okay, and now because you're hanging this mass right on a pivot, so there's no other force than just the weight mg. So actually the mg is the one that trying to pull this mass down. Okay, and because you are thinking about torque, you can calculate the net torque acting on this. All right, and if you remember, this one is R cross F. All right, but if you don't remember, that's okay. The key of the torque is the force multiplied by the lever arms, or the distance from the force to the axis of rotation. All right. So if you sort of right remember that vaguely, but that's what it is. So okay, my pivot is right here. The direction of force is down here. So all you care about is just this distance right here. That's your R right there. Okay. If the position of that CM is at the distance D away from the pivot, okay, so the perpendicular directions, okay, right, because you have to measure it perpendicularly. So the distance between the uh the force, the line of force, and the axis of rotation are separated by d sine theta. That's what you care about. So that's why the net torque acting on this mass is going to be mg d sine theta. Okay, here we go. That's your net torque right there. Okay, but that's not done yet. This torque right here try to pull this mass down in this direction. So you are trying to create the rotation clockwise. Okay, you guys with me now? Just listen for now. I mean, the conclusion at the end is easy. However, right now, you try to move your mass to the right. Okay, with me, right? The angle theta. When the theta is 0, is when the mass is sort of hanging down naturally, nothing much. And then when you move the mass away from it, you create an angle theta. Okay. However, as you can see, the direction of the theta is going counterclockwise, but this mg generating the torque try to pull this mass clockwise. So if you remember the right hand rule, the torque, you have to follow the right hand rule. So the mg is generating the torque into the page. Into the page. The torque is into the page. Yeah, you rotate your hand in the direction of the movement. Your thumb will point towards the torque vector. So the torque vector is into the page right here. But your theta is out of the page. You can think of it that way. That's a positive direction. Your theta is counterclockwise. So when you move your hand counterclockwise, your thumb point to your face. So that's why this torque is actually negative. If you think of like into your face, it's positive. So away from you is going to be negative. Things like that. So that's why you have a negative sign in the front. Okay, with me, guys? And the angular acceleration is just second derivative of the angle with respect to time. The I over here is moment of inertia. Yeah, all right, moment of inertia. Here we go. So now your equation looks like this. Almost done, guys. Almost done. Right, stick with me. All right. If you sort of confused about the torque and stuff, don't worry about it. That's not our main concern right here. The stuff that would like to sort of like I am trying to deliver to you is this. Okay. Let me rearrange this differential equation, right? This is equation of motion. All right, you guys. d2 theta by dt2 equal to, now I move I to the left. And now you have sine theta left here. This one unsolvable easily by hand, okay, because you have the theta on the right, on the left, and sine theta on the right. But I'm going to use the same approximation again. Very good. Whatever you're thinking is right. So I'm going to say, as the angle is not too bad, this equation can be approximated as minus mgd over I theta. Now you see it? Yes, I hope. Whatever stuff get differentiated twice, get back the original with the negative sign. See? Whatever in the front will represent the omega square. And you don't even have to do any solving anymore. The solution will be simple harmonic. Okay? With the angular frequency, the vibrational frequency or oscillation frequency or whatever you want to call it, square root of whatever the factor in the front, mgd over I. So this is the one that I'm going to focus on right here. So the key point of this morning lecture up to this point is this. This is college physics right here. All right. So I hope you see the whole point. All right. Very nice. Okay. So conclusion that we have. Oh, okay. That's our conclusion. The conclusion that we have over here is, I think you can, well, I always use it. So you can do derivative of anything square equal to negative something, and then you get the original back. Okay, let me sort of put that thing there. That's it. Every time you see this in your life, you don't even have to solve it. You can just say it right away. That thing, oops, sorry. That thing is this. Solution is waiting for you right here. A cosine omega t plus phi. Simple harmonic. Done. All the time. Believe it or not. Okay, sounds reasonable. All right, if this is good, all right, I'm going to conclude this oscillations and stuff in the morning with the last analysis of the energy. Okay, but this one looks so clean now. The reason it's so clean because you know how the simple harmonic works now. So when you know how simple harmonic works, you can calculate the energy in your calculation in your movement easily. Okay, just follow me right here. It's only take not so long. Energy is just coming from either kinetic energy or the potential. And what is a potential right now is a spring, because we don't care about the gravitational at this point. Just forget about it for now. So the kinetic energy is from the velocity, 1/2 mv squared. The spring potential energy is 1/2 kx squared. But now you already know what the x supposed to be. You know what the v supposed to be, because the v is just the derivative of x. So now you can see that, see, all I need to do is just substitute the solution that I had for the x. Yeah, with me, guys? Yeah, just substitute it in. And I know the derivative of this one, you're going to get omega is sine omega t. So all I have to do is just substitute this for x, this for v. Okay, with me now? But now you start seeing something right here. Okay, so what I'm doing over here is I take the x, cosine omega t plus phi with the a, square them. I get this term, the red term right here. 1/2 ka square cosine square, on and on. And then I grab the expression for the velocity and I plug it in, omega a sine omega t plus phi square. But now, remember that omega is square root k over m. Yeah. So now it means the omega square that I see in the front right here is just k over m. Okay, you guys with me now? So this omega square is k over m. So m cancel. So it turns out the factor in the front is the same on both terms. It's 1/2 ka squared. I can pull out to the front. and I only have the sine square and the cosine square left. And I hope that everyone recognized this relationship very easily. We said sine square plus cosine square equal to 1 all the time. That's it, guys. So what does this mean? It means anytime in your simple harmonic movement here, the energy of the system is constant, which makes sense because you are not losing energy whatsoever, right? Yeah, energy is the same. I mean, it's just conversion between kinetic energy to potential, potential back to kinetic, on and on. So that's why you might have some oscillation between the energy. Sometimes maybe you get more kinetic, sometimes you might get more potential, but the sum of these two stay constant at all time. Okay, so that means at any time, the sum of the two, okay, the sum of the two, you might get pure kinetic, you might get pure potential, but at any time, the sum of the two is fixed at 1/2 Ka squared, which makes perfect sense. It's a conservation of energy. Okay, so that means if I go back to my simulation a little bit, okay, so I think I'm gonna pick the old physics right here. Okay, all right, and now I'm going to show you the graph. Okay, and let me restart it one more time. Okay, see? So this curve right here that you see, the red curve is potential energy U. The green curve is a K, is a kinetic energy. And now on the left, there is a circular one, which is nice. So as I said, every time that you think that periodic, you can represent it as a circle because it come back to the original position at all time. So when I run the simulation, there you go. Let me do it slowly so it looks a little bit smoother. Oh, let me pause it. Whoa, 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 whoa. Let's go too fast. Okay. Whoa, whoa, whoa. Well, it seems like it doesn't want to take my response right now. Pause. It's hang or something. Nothing works. Oh, here we go. It's back. I get the control back. Okay. All right. Okay, let me adjust the speed down. Okay, let reduce the constant, spring constant down a little bit. Okay, here we go. So let's do this one slowly, guys. Oh. Oh, man. Can I wait? Maybe I can wait. There you go. All right, here we go. Slowly. So now if you look at this one, I mean, if you have this simulation on your device, that would be nice. So now you start seeing that, just focus on the K and the U. And now actually this is the curve of everything. So if you look at the curve on the top, from the top, that will give you the displacement dx. The derivative of that will give you the V, but everyone knows the derivative is just a slope. That's nice. All right. And then the slope of the V, you get the A. So all three of them will be sinusoidal, or I mean, it's a periodic all the time. And the energy, you're going to have the sine square and the cosine square. So as you can see, when the potential is high, the kinetic will be low. But when the kinetic is low, the potential will be high, right? They compensate each other. But the sum stay the same, as you can see from the middle curve right there. Yeah, the energy stay the same at all time. Okay, but it's back and forth between kinetic and potential. Okay, that's nice. I think. Or it's already gone. Okay, there you go. Okay, guys. So I hope you sort of see the whole picture of stuff that we are trying over here. Okay. So, all right, just go back. Okay. Just hang on. All right. Just stay with me just a little bit. So I'm gonna finalize this uh oscillations by just this. Okay, so this is for fun. All right, don't worry about it. I'm just talking and then just sort of like cool down. And after this slide, we're gonna take a break, right? So any questions so far? I think this is good in terms of like give you overview of the simple harmonic motion and uh, necessary mathematics, and actually exposed you to the second order differential equation on the stuff. I think many things is kind of nice here. Okay, so another sort of more realistic stuff is in actuality, the simple harmonic motion is not going to be just like sort of like go on forever, right? Which is doesn't make sense. You might face with some friction, some resistance, and things like that. So you can imagine that whatever stuff that we did before, instead of going on and on and on forever, you might have some restriction here, like here. You put it in a liquid, so the liquid will provide some resistance to the movements. All right. So that means over time that oscillation will die down. So this means you can think of it in terms of the amplitude of the oscillation will be reduced over time. So that represented something like this. This is intuitive. So you guys were okay, then that makes sense. Because any oscillation that you see in real life, eventually it's going to die down, it's go down to zero. Okay. However, the nice thing about this one is this. So you have to think about this material, the liquid over here. What happened if that liquid is so thick, like super, super thick, like, viscous fluid? Once you let the mass go, it might not show you any oscillation whatsoever. It's too much. So in that case, you're going to face with the black curve right here. So we call this an over-damped oscillation. So you damp it too much. Okay, damps is sort of like you sort of try to put a brake on it, but this is the over-damped oscillation. So you don't see any signature of oscillation whatsoever. That's too much. But if this liquid is sort of okay, it's not too bad, you're gonna get that reduced in amplitude. And this one you can call it in under damped. This is under damped oscillation. Very nice. Okay. But now to go over between under and over, there is a borderline that you have to go across to go from under to over or over back to under. And that we call it the critically damped. It's sort of like critical. So it's critically damped oscillation. Okay. Why do I want to sort of like put this as a conclusion? Look at the red curve, which is a critically damped. You can see that the curve approach zero very quickly in comparison to the black curve, the overdamp. The overdamp is bad, right? It takes very long time for you to get back to the equilibrium points. The blue one is kind of bad too, because you sort of swing back and forth many times in order to get to the equilibrium points. But at the critically damped oscillation, the red curve, it's sort of like die down and try to dive back to the equilibrium point very quickly. And that is your engineering frequency. I call it that. I mean, you have to engineer your system for, if you want to do like a choke up in your car and stuff like that, you want things, damp things down to the original, to the equilibrium position as quickly as possible. That would be the best that you want, to damp something down. That's why every time that you have this sort of like, think of it like in your camera right now, you have like a image stabilizer or something like that. Think of it that way. So if that stabilizer try to sort of put things back to the original position as quickly as possible, you have to put your mechanical stuff around it to have this critically damped setting, because this will lead your system back to the equilibrium point the quickest. That's the point. Okay, so that's when you want to tune your system to be the best performance in terms of, stopping some oscillation and stuff like that. You have to tune your system to be at this critically damped oscillation setting right here. All right, so there's some application right here. Kind of nice. It's engineering stuff right there. Okay, good, guys. So I think I'm gonna stop here, and that's it for the oscillations. Okay, and I hope you see. Oh, I don't know. It's a long story so far. Wow, hour and a half. Just only one story over here. But I hope you see the whole picture of going from Newton's law, write out the equation, facing the second derivative, second order differential equation. But now you can sort of recognize the pattern that every time you see this, is always simple harmonic. Once you have simple harmonic, don't have to do anything. You know it's sine, cosine, and you know all the behavior of this, right? They're all the same, right? No matter what system you're dealing with. Okay, sounds good.